Very nice introduction to what metamaterials are, and here maybe I'm going to repeat some of that. And I noticed that there are obviously some experts in the audience, and so the first part of the talk would be more like a tutorial type of review. And so if that is too elementary for some of you, so please bear with me. Okay. These some acknowledgement. And these are some of my group members who have contributed to some of the research that I'll be talking about. But the first part is more like a tutorial. Okay. So the outline. So the first part is that I would tell you something about how metamaterials can be used to control light and EM wave. And then I would tell you some ideas about what people now call transformation optics. And then I would particularly discuss some of our work on using negative index materials to do transformation optics, and of course I will tell you and define what I mean by negative refractive index. And then I would briefly discuss whether it is feasible to go from high frequency in particular optical frequencies. And then I will discuss some of our work on extending those ideas to acoustic waves. Okay. Of course, all this starts from Maxwell equations. So obviously due to James Clerk Maxwell, who probably wrote down this equation in around 1850. But the Maxwell equations there, sorry, because this is not my computer. And wow, this is a real laser. Okay. So there's something wrong with the font here, but it's okay. But actually, some people may not know that these equations are not written really done by Maxwell, because the equation Maxwell is a bit complicated, and all the physics are there already, but they are not immediately understandable to the engineers, and therefore there is in fact a very outstanding engineer with the name of Heaviside. You may have heard about Heaviside function. Heaviside function is tutor here, who's an electrical engineer who actually rewrote the equation, make it simplified, and express all of them just in terms of fields. And then the engineers immediately understand what they are, and then a lot of nice things happen. And so in fact these are should be called probably Maxwell-Heaviside equations. But even though that Maxwell is there for a century, and Heaviside wrote down those equations in around, I don't know, quite 1880. So Maxwell is there for a long time, and over a century. Now, why should we care about something a century old? Should we be, occupy ourselves with things like dark matter, dark energy, and Higgs particle, etc.? Now, it turns out that I'm going to hope that I can convince you that you can do a lot of wonderful things if you can have a deep understanding of these very old equations, and particularly bring in new ideas. And of course, all these require new advances in material science in order for them to be realized. Okay. And for example, I'm going to show you that you can have materials, you can design Maxwell equations that can make things invisible. Okay. So this is a movie. This is not a nice guy, but he can make himself invisible that you can go around and kill people, okay? And so by the end of either today or tomorrow, I'm going to show you that in fact we can have a conceptual device in which I have a man there, I can put a device there, touch the man, and then I can turn the man optically into a woman or something else. So that when you are from the outside, you look at the man, and then you can see a woman, or vice versa. Okay, or you can turn an apple into orange, or whatever you want to. Conceptually. And so I just hope you that whether they're useful or not, I don't know. Okay, but at least it's a lot of fun. Okay, doing things like that. And but before I talk about the mathematics, I just want to just give you an overview on using artificial structures to control wave, which is in fact something that is happening very active field in the past 20 years or so. But the problem is that if you want to have, do these wonderful things to control wave, you need to have wonderful materials. And some people don't call them wonderful, some people call them strange things or strange materials. Okay, and depends on whether you're theorists or experimentalists. So I'm going to tell you there are two types we used to talk about. One type is photonic crystal, and the other type is metamaterial. I'm going to tell you what they are and what's the relationship between them. And then metamaterial can do a lot of things. Okay? One thing is that it can give you a negative refractive index and tell you what we mean by that term. Now, just to tell you that in fact Maxwell is long gone, but his equations are still generating a lot of new knowledge. And so this is something that my student just did it for me a few hours before I bought my plane. And I found it quite amazing that just on the topic of photonic crystals, okay, you can see that they are still very active fields, okay, generating almost 2,000 papers a year now. And metamaterials is a somewhat newer topic, and then transformation optics is again picking up. And so these are very old stuff, okay, that's a kind of a new life if you have some new ideas that you can bring into it. Okay. Now, so let me start from telling you something about photonic crystals, which probably is these modern electromagnetic materials. This started in about 1987. And so this is a picture taken for a micron scale photonic crystal, and this one probably operates around 2 microns. Okay. Now we notice that this is a periodic system of dielectrics which can scatter away. Okay. And whenever you have something that is periodic, and then of course we can use a band structure, okay, dispersion diagram, to describe the dispersion properties. And a typical one would look something like this. Okay? And you see that, well, what's so exciting about this? So basically, if you can control your dielectric structure so that it's periodic, then potentially you can get something like this. But then there are a lot of things that's interesting, because you see that, of course, it is not electron. Electron would be parabolic here, light would be linear, okay, because we have no mass. But then if you can control the structure there, you can change the slope. Okay, that means that you can control the speed of light there, and you can purposely break the symmetry so that you can even change the so that you have different polarization can have different speed, and then you have what we call formed by refringence, and you can even make it sensitive to circular polarization. Then you can have circular by refringence and circular dipolarization. So a lot of things that you can play around just in one wavelength limit, and then of course when you go to the wavelength in which wavelength matches to scale, then you have very strong backscattering. In that case, in some cases, this backscattering can be so strong that you open up a band gap. A band gap means a place in which you have no mode there. And so if you look at the density of states, and then you will have something here, and then there's nothing particularly interesting up to there, you will see a very high density of states. Okay? And then suddenly it will go to 0. And of course, if you can control density of states, there are a lot of things you can do, because by the end of the day, how matter couples what in fact depends on what is density of states in the medium that you're talking about. And therefore you can control a lot of optical processes by controlling density of states. Okay? And if you go a bit higher, you can see that even the slope of the bands can be negative. If you look at what it means, slope's negative, that means the pointing vector and the k vector, they're pointing in different directions, and then you can do a lot of interesting things, creating patterns. So there are a lot of things you can play around with these type of structures, okay? And of course, initially when it was suggested by Bonwich and Gifton, they're thinking about how we can modify density states to control optical processes, and then you can also control what we call photon localization, which I'm not going to talk about today. There are lots of possible applications you can think about photonic band gap, which I'm not going to go through them because it's not of main interest today. But this will show you some nice pictures that I steal from the web, and there are different ways that we can make these structures. Okay, if you have a big budget, and you can use EP machine and so on, and then you can these what we call top-down basically fabrication processes. Okay. More or less like when we make a CPU chip, it's the same process. Or if your cameras go to a beaker, you can mix things up, self-assembly. Okay, you can also make these crystals. And these are of course 3D, but then you can also do it in slabs, quote-unquote 2D type. And in fact, these are coming into real applications very soon. And then you can do core C1D, optical fibers, in which you have infrastructures, so that you have some people call them holy fibers because there are a lot of holes there. And then the nice thing about this is that you can guide that even in the empty space. And then you can do a lot of these things. Okay. Now, But of course, what characterizes photonic crystal as an artificial material is that the wavelength basically is more or less the same scale as the structure. Okay, but if you have a case in which the wavelength is much bigger than the structure, but then you still have a lot of interesting features there, and then we typically call them metamaterials. And so if you look at how they are defined, and then say metamaterials are basically artificial composites. Composites because they are typically multi-component. Okay, artificial composites are exhibiting interesting properties, superior in some cases, which is not observed in the individual components. So we have to make a structure and mix different components because we can achieve them. And these, in fact, are coming from the inclusion. Now, what distinguishes a metamaterial from a photonic crystal is not just the scale, because for photonic crystal, what happens here is that these can be very uninteresting by themselves. It is by the structure, by the way that they couple of light, by gas scattering, that give you all these interesting gaseous state changes and so on. But here, for the metamaterials, such as the other way around, the length scale of these are not so important. It is basically the structure of the individual element inside, the resonances that give you all the functionalities. Okay? And so distinction is there. And of course, metamaterials, I'm going to tell you later, is going to do a lot of funny things for you, including the possibility of giving you all kinds of illusion. But all underlying all these, the important thing is that with the metamaterial, with all these tiny resonators being embedded in the holes, and they can give you all kinds of the values of the permeability and permittivity, okay, the response to E field and B field, and to the extent that it can give you negative values, and these negative values are typically for some frequency in which the resonators are resonating with the incoming wave, and in fact it can be so. I'm going to tell you right away that if these are what we call epsilon and mu, if they're negative at the same time, then in fact we have something called a negative refractive index. In fact, in principle, just about any value of epsilon and mu can be obtained for some frequency if you are able to manipulate the material and the microstructure. Okay, and I'm going to show some examples later. And so again, for those of you who are not for equations, the time to take a short nap, but these are very simple. And so just to show you that what is the consequence. So suppose if I have a metamaterial that the mu and epsilon, I can make them negative. Now, what can you get out of them? These are the Maxwell equations. Describe how the wave couple to each other. And the material properties are basically all swept under the rug by two parameters, epsilon and mu. And of course, if you get a really gigantic supercomputer, in principle, you can even compute it with quantum mechanics. But in classical physics, you don't care how they come out, just measure them. And so the epsilon governs the interaction with E field, and mu governs interaction with magnetic field. And now suppose that all these structures are so tiny that you don't see them. Okay, so you only see the effective parameters. Now in that case, I still have an effectively homogeneous system, and then which we have plane wave solutions. And of course, for plane wave solution, we know that the what we call the dispersion, which is the relation between the k and the omega, is given by this relation, which is just the product of epsilon and mu. Okay, and of course, in standard textbooks, we simply call them the n refractive index, which is given by n equals to square root of epsilon times mu. Now, look at this equation, and we say that for materials that we are familiar with. Now, of course, epsilon and mu are both positive, and in that case, the k is a real number, and then you have a propagation. Okay. Now, but if one of them is negative, say if epsilon is negative, the other is positive, or the other way around. If one of them is negative, then you see the k squared becomes a negative number. That means that k becomes an imaginary number. Okay. So k is a complex number, and that means that you have a decaying wave solution. And so if both parameters are positive, you have propagation. If one of them is negative, then you have decaying wave solution. Now this is well known because it's what we call plasma, right? In the plasma, below the plasma frequency, you don't have propagating wave. But what if we can have some structures in which both of them are negative at some frequency? Both of them negative, then k squared becomes real again. and therefore you get a mu solution. Okay, and therefore you get a propagating wave. And so one negative, no wave, two negative, no wave, but both negative, you get a wave again. But that wave has an interesting property because in that case, the n becomes a negative number. N negative means that if you have a light coming in the interface between the positive and negative index, then the light is going to bend in the wrong direction with a negative Snell angle. Now, and another thing which is interesting is that if you look at this equation, if I transform to the Fourier space, I can do that because I have a plane solution. Now you can see that for material, the ordinary, when mu epsilon is positive, then epsilon mu, and then E, H, and K form a right-handed set. It's well known in textbook, right? But it happens that you have a propagating wave with mu and epsilon being negative at the same time. Then you will see that, in fact, you see a propagating wave solution. But then, if they are negative, then it turns out that if the positive number gives a right-hand set, then if they become negative, they have to give you the wrong sign. That means you're going to have the K is going to go in the opposite direction. But the product, the cross product, E and H, give you the pointing vector. And that means that for these material in which you have a metamaterial in which both epsilon and mu are negative at the same time, then the pointing vector, which tells me where the energy flows, and the K vector, which tells me how the phase accumulates, are pointing in opposite directions. Okay? And so this is one of the very special property of this, what we call double negative materials. And in literature, it's very frequently called left-handed material, simply referring to this phenomenon. But I just want to remind you that this term is a little bit deceptive because we have handedness usually when we talk about either a spiral or chiral. Here, nothing is spiral, nothing is chiral. The so-called left-handedness simply refer to nothing more than simple this statement that K and S are pointing in opposite. That's all it means. Okay. And so, in fact, engineers in some cases simply call them backward waves. I think it's probably a more scientific, accurate term than left-handed material. So, to say no plus no equals negative, yes, okay. One negative, no wave. The second negative, no wave, but both of them negative, you get a wave propagating, but it goes in the wrong way. Okay, just in the opposite direction. You say that, well, who cares? And then the funny thing is that if you have a epsilon mu negative at the same time, you get a negative n minus 1, and then you can show that, in fact, this thing, your perfect lens. Perfect lens means that if you have a lens there, a point source gives you a point source. And I think I'm not going to too much into it because Zhao Wei has already discussed concept behind this. Okay, and but the important thing to know about the important thing about this is that that this is not just a point-to-point focusing. In fact, the image, okay, if you have a perfect, really perfect super lens, in fact, have a perfect resolution in the sense that it is not bounded by the resolution limit, simply because of the fact that the negative refractive index with mu and epsilon equal minus 1, as I will explain to you, that it supports, in fact, surface wave, both the TE and TM wave, and in fact, at one frequency for all wavelength, for all K vectors. Meaning that, in fact, all the information for the source will be transported to the focus. It's quite amazing because if you look at Maxwell equation, even vacuum, if nothing there, vacuum is in fact a low-pass filter. Okay, it filters out the high frequency. But if you have a negative refractive index, in fact, it compensates for all the losses of the resolution there and give you that. And so it is something that is rather amazing. And, but of course, initially, in fact, it was as early as in the 60s, as Russian physicist named Vasilako that raised all these ideas. But it takes a long time. It's until Vasilako who actually proposed that in a paper, and it talks to the 1D801 because before these materials are really made, And what enables that is the possibility, in fact, to create a negative mu. Because as I said, in order to realize this metamaterial, you require epsilon and mu to be negative at the same time. Now, negative epsilon is not difficult because you're talking about responses to electric field. And electrons naturally run electric field, and therefore you can all have what we call plasmonic or plasma responses that give you a negative response as long as the frequency is below the plasma frequency. But there's nothing really called magnetic plasma, okay? And therefore require some artificial structures that give you a resonant response to the magnetic field before you can get negative mu. And then it was due to Pentry and Davis and that we designed this what we call a speed ring, okay? That give you that. But of course, these are the early proposals. There are a lot of other resonators can give you also resonant response to magnetic field, as Professor Zhou have shown you his very fancy fractals can do the same. Okay? And of course, if you have these, they typically have one strong magnetic resonance. If you have a fractal, then you have a distributed resonance for multiple frequencies. I just want to show you that this is not just a talk, but they really measure if you have negative refractive index. So they compare two systems, one with positive, one with negative refractive index, and you can see that in fact, if you have a prism, okay, light goes to the wrong direction. Okay, the positive goes to here, negative go to there. So it is very well controlled. And just a summary for this part, I just want to compare. We heard about photonic crystals, metamaterial. What is the difference? For photonic crystal, basically you have structures in which the lattice constant is roughly the same as the wavelength, while for the metamaterial, the wavelength is typically much longer than the structure, and therefore you pretend that you don't even see the structure, you see a quasi-homogeneous medium. And now, of course, for photonic crystal, you can also get negative group velocity, as I showed you in some of these earlier. You can also get negative. But this is a consequence of scattering, backscattering. Okay. But for the case of metamaterials, and these in fact come from resonances, subquantum resonances, and which give you a effective negative mu and epsilon. Okay. And of course, for the photonic crystal, we use band structure description, while for metamaterials, we use something called effective medium, or in a way that we pretend that we cannot see the microstructures, but all the physics are described by the what we call these the constitutive parameters which are used. Okay. So now material, of course, a few years ago you will see that when people mention metamaterial, they all talk about negative refractive index. But now today, metamaterial has much broader sense. I would say that anything with some unusual values, epsilon and mu, and this comes from artificial composites, people call them metamaterial already. Okay. Now after telling you there are great advances in mixing artificial materials, and now I'm going to come to the second part, which I'm going to tell you that if you have these materials, you can use a new concept which is called transformation objects. Okay. And then you can design very crazy things. For example, you can design a shell in which all light comes in will be guided around the shell so that there is a certain region inside that light never comes in. And thereby you can make a certain region, okay, invisible. And all this, in fact, comes from some very interesting properties in Maxwell equation. It turns out that Maxwell equation are what we call form invariant under a coordinate transformation. Now, this statement will not mean much because we have seen that in textbooks many times, and it's taken as a fact. But I'm going to tell you that if you understand what this statement means, there are a lot of really funny things we can do about that. And so mathematically, the textbook will tell you that this is Maxwell equation transformed to, assuming that we have harmonic time dependence. And you say, let me perform a coordinate transformation, okay? And then you can show that, you can see at this paper that derive all this for you, that if you do that, then in fact Maxwell equation have the same form as long as you transform the parameters at the same time. But then you say that, what does it do for you and what is the real meaning? Now I'm going to take you through a short tutorial to see exactly what do we mean by this statement, and then what can we do with it. Now let's start from something very heuristic. Okay? And you know that in optics, no matter whether you are going for classical optics or in wave optics, it is the phase of the optical path that determine everything, right? So let's suppose you have a material that have a distribution of refractive indexes, and so that when the light go through the material, at each point you accumulate phase, which is given by obviously nkx delta x. Okay. Now, of course, in textbook they tell you that, well, of course, the wavelength is changed, but there's no reason why I cannot put the n there. So they say that, well, my k has not changed, but in fact my delta x has changed. And therefore, one way to see that, to interpret this, is that material which carries refractive index, and in fact, I'll be normalizing your scaling as far as light path is concerned. Or you look at the wave equation, okay, just one of them, and you can always write something like this. And this is a differential operator, and therefore this is some ddx, ddy, and ddz. Or whatever. You can just say that the Maxwell equation is the same as the freeway, as nothing is there. If I insist that in fact there's nothing there, but in fact my link skills are redefined. Okay. And so this is in fact all the concept behind what we call transformation optics. So now let me put it in a little bit more concrete example. Let us use the simplest possible transformation that we can talk about. It's a linear transformation in one dimension. Suppose that I have an x, y, z coordinate Cartesian, and then let me change the scale in just one dimension, so that I change the scale. Okay. And here I choose the scale to be less than 1, but it's arbitrary. It can be big, it can be small. And then let me insist on something. Let me insist on, now if I change the scale, let me insist on, in that scale space, let me put in something, but I want to have the, whatever I put in, I want to have the effect that the wave coming through that path is the same as if I haven't done anything. Okay. You say that, is that possible? Okay. And the answer is, in fact, yes. Okay. Now, in fact, this argument was initially due to Professor John Pendry. Okay. And he said, let's look at this system in which part of the space, the blue part, has been rescaled by a scale length A, and then I'm shining a wave in there. My requirement is that I want to put in material so that nothing has changed. Okay? And therefore, before I do the scaling change, the phase change should be k naught, which is omega over c. Simply what is the k vector in free space times the distance d. But now that for this part, I have scaled it, and therefore the distance becomes a times d. Okay? But then my k is changed by n times k naught, where n is square root of epsilon and mu. Of course, as white is a transverse value. The epsilon and mu are those epsilon and mu, the tensor component in the direction that are perpendicular to the k vector. If I insist that nothing has changed, the same goes, then the consequence is that my epsilon and mu in the perpendicular directions must be 1 over 8, right? This offers. Now, but this is just for one direction. Now, how about the other? Now, for this direction, notice that the spacing is the same. I haven't done anything. And therefore, the phase change, if I again insist that the phase change is the same if I've done nothing, then the phase change must be the same as free space. And of course, nothing has changed. But then I've materialized it, okay, and therefore must have refractive index again is given by the square root of epsilon and mu, okay, and again these epsilon and mu are for these components there. But notice that I have no choice but already say that one of them must be 1 over A. And since one of them is 1 over A, but then I require that nothing is changed, then the other one must be A. And so this very simple argument, and then without doing much mathematics, and then you can say that if I'm going to perform a scaling, and then if I insist that this scaling doesn't change anything, and then I must change my epsilon and mu accordingly, according to this particular tensor. Okay? And so one component is the same as scaling, but the other two components are the inverse of that. And in fact, if you have put in such a parameter into this space, okay, then you will see that what happens to the wave is exactly the same as if in free space. And you see that, well, this is just playing around with mathematics, but I'm going to show you in a few minutes' time that the same argument always requires that you change from a Cartesian coordinate to a circular coordinate. Then you can create an invisibility clock, and you can do Harry Potter stuff. So let me just show you some numerical simulation. For example, in space, for example, divide space into 3 parts. One part the same as the air, the other part is scalar. The third part is that I could go back to air, and then the material parameters look something like this. And so I could do a simulation for you. And so this is a part in which I have a region with 4 units, okay? And I'm just passing a Gaussian beam through, okay? And now here I purposely would contract this region by a factor of 2, okay? So there's only half as thick. But then I put in this tensor there, okay? And put in sensor there. And I'm not going to tell you how this can be made, but supposedly it can be made. And then it turns out that the wave passed through, but then but if you overlay, you find that this part is the same as that part. And therefore, I can use half the space, but I can do the same for you as if I have free space. But then you see that it sounds quite okay for a theorist, but in fact, you can do these fancy things, but there's no free much. Now, in fact, even this very simple transformation would end up with something that is highly undesirable, I would say, in terms of experimental realization. Now, first of all, you will see that for normal material that we are familiar with, these epsilon mu are usually given as a number, okay, and because they are isotropic. But now, once you do a transformation in the physical space where the transformation is being executed, the epsilon and mu becomes a tensor. Tensor meaning that the response in x, y, and z directions are no longer the same. So you have what we call an isotropic material. Okay. And also you have very strange values, epsilon and mu. And what do I mean by strange is the following, that if you want to have a bigger than 1, then this will be less than 1. If a is less than 1, then this one is going to be less than 1. Okay. And you say that, well, what's the problem? The problem is that in nature, it is easy to find material that epsilon bigger than 1. Anything that you can touch here, including water, glass, whatever, epsilon are always bigger than 1. And there's almost nothing in nature that epsilon is less than 1, unless it's less than this. Okay? And therefore, so once you have this, then you have some very unfriendly material that you have to make by hand. And generally, the transformation of the scale does not have to be uniform, and therefore, in most of the cases, you know what we call an homogeneous material, position dependent. Okay, second very top. And probably the worst among all is that we require to have a mu. And for those of you who are in material science, you know that epsilon can take up all the values because of the fact that electrons are responding very quickly to electric field. But electrons have to go around a circle before it can respond to magnetic field, and the response is very slow. And therefore, mu is usually an uninteresting number, and put this way, in particular high frequencies. And therefore, if you require mu to be there, to be a tensor, and then it's very difficult. And such materials simply do not exist in nature. And that's why I have to give you an introduction about metamaterial, and all these realization would require the fact that we can do some man-made material and have all these funny values. Okay. Now, just as a side note, I would say that we can do wonderful things if the refractive index is -1, in which the mu and epsilon -1. Now, in fact, for that, it's conceptually very simple. You just change the scaling a equals to -1, okay, and then you can end up with a negative n -1 stuff. So. And of course, now as I just want to say that with transformation optics, you can do a lot of interesting things, but unfortunately, I think that in nature, when all the optical properties come from atomic responses, you don't have much that you can play around with. And so you rely on all these fancy things. This works on microwave, terahertz, and this is almost up to optical frequency or the Fishnet that you require that you can achieve all kinds of instrument view that can do these wonderful things for you. Now, I'm going to tell something about heuristics, the refractive index, change the length scale, and then be a little bit more rigorous tell you 1D how that's been changed. Then I'm going to tell you what happens in 2D. And in fact, after working through the 2D example, we will immediately arrive at how we can do a invisibility cloak. You can become a Harry Potter. But I think before I do that, maybe we should take a short break here, and maybe I can take a few questions before I go on to the equations. And by the way, if you hate equations, you can take a longer coffee break, okay? Because I have about 10 minutes about equations.
Questions, please? Other questions? Well, if no questions, then we will reconvene after the coffee break.
And since we are talking about something with cylindrical symmetry, and therefore we choose to use the epsilon c mu theta and mu r. So this will be the differential equation, Maxwell equation. Okay, that when you put in a computer or if you are super with your special functions, and in some cases you can even solve it by hand. Okay, but I'm not going to solve anything. So I'm not even going to tell what these are. These are some numbers. Okay. So what I'm going to do now is do something. I want to change my coordinate system from an R to some function fr. The only thing I assumed fr is a nice function. Okay, it behaves well, so that I can do differentiation and so on and so forth. And so once you do that, we say that this equation will become that. Okay, if the f prime is still good. Now, of course, these two equations are no longer the same equation. Okay, and therefore, if you solve this equation and that equation, in general, you get different answers. But then I'm going to see that I purposely make some coloring. Because somehow the color is green is not the same as the color on my computer, but I think that they are the same color, right? And it's all the same color and the same color. I'm going to do something, so that I'm going to do some transformation on this epsilon c, mu theta, and mu r. And you see that I'm going to show you within a few seconds, maybe a few minutes, that there exists some transformation that I can transform this equation back to that equation simply by scaling my epsilon theta, epsilon c, mu theta, and mu r. By scaling them, I can make this equation go back to that. So first of all, let's compare. I'll compare this term with that term. So, and after transformation, one of the term looks something like this. I want to compare this and that, and I want to ask myself how I may transform this back to that. And to say the answer is simple, you see that if the mu theta have this particular form, which depends on the function, of course, and derivative, then it turns out that this part would become this, which formally is the same as this derivative. So put this in mind. Now, and also I also want to change epsilon c to rescale the function so that it becomes something like this. Then it turns out that this becomes that. Okay. Now, if you say that what have you done? Well, basically by scaling this number and that number, I basically make this function the same as that one already. And then I noted that since I already have chosen how to scale the epsilon c, okay, and then it becomes something like this. Then you say that if I change to scale mu r in such a way, then this function will become that function. Now you see that I'm going to be going a bit fast. as in the classroom, I need to do this more, but I want to leave the PowerPoint behind, and you can just follow all the math. Then you will see that as long as I do this, and that, if I redefine this wave function, then this second order differential equation, okay, which is the consequence of changing the local coordinates from in R to an FR, then this function, as long as the epsilon c is that, the mu R is that, and the mu theta is that, then this function will become this. Now notice that this function is exactly the same as that. It's just rewriting the R into the F. And then say so. Okay. That means that in fact this equation, since it's formally the same as that equation, that means that whatever solution you can put on your computer or by hand you found, is that would immediately be also the solution of that equation, with the only consequence that you change the R to the function F. Now you say that, well, if you really work that out, you say that, well, this is nothing but just a mathematical game, simply a coordinate transformation. You say that what have you achieved by playing such a game, which could be as well be an exercise in mathematical physics class. Okay? And you see that, let me do the following. Let me have a domain, and I draw a circle there, and this is in a 2D system, okay, so that anything along the z direction, which is out of the plane, is invariant. And then let me have some area. So this is just simply just this coloring is for have no physical meaning, just a mathematical. So this is just a domain. Now let me define a certain function that change the local coordinates inside the grain domain to the function f. So r theta, the theta is unchanged, but r becomes an fr. If I do that, then you will see that, of course, in the r theta, the r is 0 as origin. But now when r is 0, it becomes, so the function is 0 and r is a. So this function, or transformation, while preserving the theta being unchanged, is what mathematicians, they call them a push-out transformation. So basically, I push the central point into a circle, and then all the other coordinates are deformed radially adiabatically. And so I deform something like this. And of course, you say that so on. And then the few slides that we have above is so that if I have material inside this region, okay, and they satisfy these transformations, okay, mu theta equals to r times f alpha f. Then the differential equation with this coordinate is exactly the same as here, and therefore they obey the same solution. But if you spend 5 more seconds, or maybe 5 more minutes thinking about what is the mathematical implication of that, that means that whatever solution I found here, I am no longer required to do anything, because they are the same equation simply by replacing r by f. Okay? That means that all the rays I can trace, I can just trace the ray, but I trace the ray in my deformed coordinates. That is, if I have some light coming in, of course, because this is free space, light will just go in a straight line. Now if I have a material shell that obeys this equation, the light will follow adiabatically my deformation, and therefore will go something like this. That means that light would in fact go around the circle there, and will never reach that circle. So with this type of parameter in here, light will always go in this up. The important thing is that this is correct for any type of incident wave. I don't care whether this is a far field source, plane wave, a point source, 2-point source, coherent, incoherent, I don't care. Because for this case, light will just go straight through and light have to go around this space. And therefore this space would never be accessible by your external light. And therefore, this region is in fact invisible. And also, if you have an observer here, people will always see light as going through a straight line. Okay? And therefore, when people think that there's nothing here, people would also think there's nothing there. Okay? Because it will find the light will just go straight through. And therefore, this region will become perfectly transparent. And therefore, if you put yourself inside, you will become Harry Potter, because other people will just see through you or see you. And thereby, just by this very simple transformation, you have achieved invisibility. And therefore, if you maybe during the coffee break, a couple of young friends already told me that they have seen in the internet discussion about invisibility, of course, coming from these transformation optics. What they are talking about, of course, they will make the math a little bit more obscure so that you don't know what they are doing. But all they're talking about is nothing but this transformation. And so by this very simple transformation, we know believe in how we can achieve invisibility, okay, in the mathematical sense. And of course, now just to recap, why is it invisible? Simply because, first of all, no light enters this region. And secondly, in fact, the light path after passing through the cone is exactly the same as if nothing is there. Okay? And therefore, you think that that region is invisible. And also, what is nice about this is that, in principle, you can put anything inside this domain. You can put a cow inside the domain, you can put a Harry Potter inside the domain, you can put a jet fighter inside the domain, and that would not be visible, because simply no light will enter that domain. As long as that object can be entirely be encircled by that domain, it will become perfectly invisible. Now, but I'm going to tell you that it looks nice, but there are a lot of things that are not that nice later. Okay? For example, all kinds, this kind of thing, I have limited bandwidth and so on, but I'm going to talk about that later. But for the moment, let's be excited and say, okay, we have been able to make things invisible. And of course, now I'm going back to the side of social, that if you look at the Newton's paper, and you can form all this in terms of the coordinate transformation. Okay, but if you adapt this to the particular case of a 2D spherical case, and then you just end up with these parameters. But again, that light is not that simple, because if you look at that, then you will see that in order to achieve the invisibility, even for this very simple case, then you would have a tensor, okay, use a tensor, and these tensor take up very weird value, okay. Look at when r equals to a, in fact this goes to infinity, and this goes to 0, okay, and therefore you have to have very strange parameters before you can achieve that. So, so this is the transformation that takes a point R to a finite radius, and then and here you just match to the boundary. And with this transformation, okay, for the Kurzweil transformation, then you can achieve invisibility. Now, if you trace who did what, it's kind of funny, because in 2006 there are two papers in Science, which is back to back, and come the same time that propose. This is basically due to Pentry, but Leonhardt also have very similar, but he works mostly from the perspective of the geometric optics limit. Okay, but the result is more or less the same. But if you trace, in fact, the mathematicians in a few years back have thought about the same problem in different contexts, and they have arrived at quite similar results. And if you look again, that in fact, it turns out that people said that in Russian literature, in 1961, people have already written equations that are similar to that. I've not been able to read that paper because I don't understand Russian. That paper has no English translation up till now. And so, and if you look at it, it's kind of interesting because John Pentry is, in fact, in the old days, to low energy electron diffraction. So the solid state physics is Leonhardt is a field theorist working on general relativity. Okay. And of course, Greenleaf and Masters and Ullmann are mathematicians, and they vary about inverse scattering problems. And I think this gentleman is in fact an engineer. And so you have all people, okay, converging on this same. But you say that why would that catch attention just now, but probably not a few years back, maybe not in 1961. And that is because all these values can work out the mathematics in a short time, and the conclusion is that the parameters required to do the invisibility for you are outrageously difficult to make, and they simply don't exist in nature. And that's why in the old days this would become mathematics, and in fact these are practitioners. And it's only in these few years that people can really make those things and then make things realizable. Now, so just say that this code is what we call perfect code, and because it cooks everything. Anything you can hide inside the domain would be invisible. But I'm going to tell you that in fact we can beat that in some cases, and that will be what we're going to talk about later. And it's for any kind of wave, okay? I mean any kind of interwave. And it's rated in both wave limit, and it's a passive device, okay? This is a device that can make things invisible, does not require any power, does not require any artificial intelligence. It will do it all for yourself, by itself. Now at this point I do want to say something which may be obvious to some but may be confusing to some other people. Because what we mean by invisibility, in fact, could mean different things to different people. And now in fact you can make things invisible by chemically changing something so that the refractive index becomes 1. Now this is in fact something that was suggested in a book, I think called Invisible Man, that you can drink something that makes the refractive index equal to 1 and thereby make itself invisible. And there will be chemical means, but there are no drugs that can do it so far, and if it exists, I don't think you want to drink it because it will probably kill you because of such a drastic change. However, in fact, somewhat later, there is a concept called the invisible woman that can create some kind of force field around herself so that anything could just go around herself, including light. Now this would be a physical way of doing visibility, and this is precisely the way that we are now doing visibility with these non-dimensional objects. So we are doing it basically the invisible woman way. Okay, and of course the final outcome would be something like this, and which is taken from a movie called I think Data. How many of you are from California? No one. Not even one. You may recognize this gentleman, right? And who used to be a guy who kills all kinds of aliens and now becomes a California, the boss of California, the governor of California. That's what's in there. So we are basically doing something like this. But the thing I want to distinguish between this invisibility is entirely different from so-called invisibility concept in war technology. Okay, I'm sure that you have seen pictures of this F-117, a US fighter that is invisible to radar, but operates on an entirely different principle. The thing that this becomes invisible is because of these flat, big, and angular surfaces. So that the radar comes in, it gets refracted to a wrong direction, so that the receiving radar will receive it. And also the surface is coated with very absorbing microwave absorbing material, and therefore it doesn't reflect that much anyway. And therefore, strictly speaking, these, that, and that, okay, that you use to kill people are not an invisible object. Strictly speaking, they are what we call a dark object, okay, meaning that it doesn't reflect the radar in the direction you want it to reflect. Okay. But however, if you have a radar on the sky, okay, you have ARA or something that you illuminate the object from the other direction, then it will cast a shadow, and it becomes irresistible. Okay, and therefore, while the invisibility that we are talking about here is in fact making things perfectly transparent, so it is another thing. So what we talk about in technical terms is that we are designing something that has zero extension cross-section. Okay, while this has a zero differential refraction coefficient in one particular direction, so these are very different things. And of course, you can make yourself invisible by doing camouflage and invisibility that we talk about have nothing to do with this. And another thing I want to distinguish is that you may have seen this many times in the Discovery Channel or something like this, which is Japanese technology, which is wonderful by itself. Exactly how they do it, I don't know, but supposedly that they have a kind of a very smart code that is what we call retro-reflective. Okay, and they have a camera that will do some filming of the image behind, and then they take the image in the front, and then they project the image back to the code so that you appear to be visible. Now, And of course, in the ultimate limit, you can probably have the illusion of being invisible, but he is invisible, but all these instruments, the cameras, projectors, and so on, are very visible, okay? And also only works for one single direction, okay? If you check your hand, it won't work. And therefore, and it also requires power. You have a lot of things, camera, batteries before it works. So it is an active optical camera, it's not invisibility, okay? And so I just want to distinguish between all these confusing terms. Because when I gave a talk, some people thought that we are emulating Japanese, and we are not doing that. And so this is a numerical simulation, and to show how it works there. And for example, just put in a metal cylinder there, and of course light comes in, it will be scattered. And if you enclose the cylinder with the shell that designed using precisely these parameters, okay. And then the plane wave just pass through the object, no scattering. And therefore, if you are there, you will find that nothing is there. And you can hide almost anything inside. So all these are just talk, but can then be realized experimentally. But the answer is yes, okay, it can be done. And in fact, it was a really, truly beautiful experiment done at Duke by David Smith's group, that they use these speed ring that create the resonance source for the mu r and mu theta, and then this is a 2D system of layers, and you can see that the invisibility is achieved kind of approximately. Of course, this is the case when the system is ideal. When you make something, you can never make it ideal, but you can kind of see roughly the fact that it almost like a plane wave refund after it passed through the object, and therefore. Just want to show you this particular slide to show that we're not just talking about something mathematical. It can be done in microwave in some cases. Okay. But for those of you who care for the details, you will see that the light only achieve a perfect cropping, and that is because the parameters that is required are so weird that it is not so easy to make. And so what the experimentalists decided to do, they wait for a very long time. They want to publish a science, right? You have to do it quick and fast. And therefore, they do it with what they call a reduction. Or what we are doing is a structure that is kind of similar to the perfect crop, but not exactly. Okay? And therefore, they will achieve the effect approximately, but not exactly. And the idea, and in fact, almost all experiments you can see these days are what we call reducible. And what the trick is that you try to keep the same refractive index variation, but then you give up on the impedance matching. And therefore, it will cause some scattering, but it will still do the light steering for you, more or less. And I'm not going to go into details, but if you look at the equation in 2D, you will find that, in fact, if you can maintain this product and that product, which incidentally gives you the refractive index tensor in two directions, to be the same. In fact, the light steering property will be exactly the same. But what you gave up is that you have some mismatch, impedance mismatch in the surface, and therefore you would scatter some wave in the surface. And therefore it reveals the surface a little bit. But if you are going to do that, you see that if you only require these two numbers, the product will be a particular constant. You have a lot of variations to choose your parameter, and therefore you have a lot more room to manipulate, and therefore you can do the experiments quickly. Okay? And so this is just one I want to tell about some details. And I just want to tell you that this effect is basically a mirage effect. I'm sure you know what a mirage is. A mirage is such that when you have an air which is hotter of the ground than the sky, and then there is a gradient of the refractive index, and therefore light comes in and then it bends out. And then you will see something like reflection of the sky, you see there's water, you walk there and then you die because there's no water there. And this is more or less the same. Okay? And so it is the gradient is doing the light bending for you. Okay? Except it's a perfect mirage in the sense that it gives you a perfect illusion. Okay? Now, so I've talked about what transformation can do for you, and therefore, in fact, I told you that just a very simple radial transformation can do invisibility. Now, from now on, I'm going to tell you something about the research of our own group that play around with all these transformations, and I picked my own group stuff just simply because all these are ready and just grab some slides and can do that. Doesn't mean that there are not other. There are in fact a lot of other important papers. You can just go to Google Scholar and you type in transformation objects. You will find a really huge number of papers, and then you can read them for fun. And so I'm just going to give you a small subset that I know better. Okay. Now, so the first thing I want to tell you is that this so-called push-out mapping, radial transform, can create illusion so that the domain becomes invisible. And then I ask myself, what if you have in fact not a radial transform, but in fact an angular transform? What will it do for you? Okay, and so this is one of the things I want to do. Okay, and so it turns out that you will create an illusion of a rotation. And so the mapping is there. And you know that this mapping is formally the same as the radial mapping, but now instead of doing it on the radial coordinates, I keep the radial unchanged, but I apply the mapping on the angular coordinates. And so the coordinates would be distorted in such a way. And then, of course, you know the general equations, and you can put on your Mathematica, you find it out. Not going to tell you details because you will really be boring, but just let you know the consequences. But anyway, with a few minutes of computer time, we can determine all the numbers and show you what it does for you. So what it does for you is that this is the shell with these parameters designed by the angular transformation, which is equivalent to an angular rotation. So the plane wave comes in, it sees the shell, and it rotates the wavefront so that the interior domain, okay, the wavefront returned by a certain angle. In this particular case, I choose the angle to 90 degrees, but after that, it comes back and then go back into itself. Now, so what happens is that an outside observer will see nothing has really happened, and therefore it will not even know that you have a shell there. Okay, this shell by itself is set invisible. Okay, so it's an invisible shell. And this invisible, what it does for you is that it turns the wavefront by a certain angle. And you say, what is the meaning of that? Now, that actually means that now the world becomes rotated inside and outside my invisibility of this rotation device. And to be more precise, let me put an object there. And this object is purposely chosen to be have such a shape so that it has very small scattering in this direction, but have much more scattering in that direction. So that if I, for example, if I would choose to rotate an angle, I would see a much bigger cross-section, simply because this is big and that is large. Okay. Therefore, I expect that if I change here, I should see a very big scattering. This is what I've done. I changed it. Okay. And since I have changed the object by 90 degrees, I should see a much bigger cross-section. At least I should not see the same cross-section in this one. But now I put my invisibility rotator there, and since my rotator rotated wavefront by 90 degrees, and so here I rotate 90 degrees, I can rotate the inverse 90 degrees so that I can compensate for the rotation. Now this is a real rotation. This is a wave rotation. So I use a wave rotation to compensate for my real rotation. So that after you do this, the wave coming out is exactly the same as if I have done no rotation. Now I just want to remind you that I should have seen a much bigger cross-section. But by putting in this device, I actually would have the same cross as if I had not rotated. Okay? But the device itself is not detectable because it does not cause any scattering by itself. And so what I've done is that I have created another kind of illusion. Now for the radial transformation, what I've created is illusion such that if you see nothing there, there may be something there simply because I could have put a shell around it to hide it from you. So that you see nothing there is not a conclusive evidence, nothing there. It may be something there. It may be something with the shell. Now with the rotation, I could create another kind of illusion that you may think that I am facing you, I'm talking to you. But in fact, I could have facing this direction. As long as I have a shell around myself, I can control how I appear for you, so that your eye will see a rotation. a rotated world, but you would not know. But of course, I will also see a rotated world, but I will not know that you have rotated, okay? And it's mutual. Now, another thing is important about all these things that come out from transformation optics is that it does not depend on the source. And I just put in a particular case in which I have a point source that without this device, the light should go in this direction, but now with this source, I'm going to have to change the wavefront so that whoever inside will thought that your point source is coming from there. Okay, so now after that, I'm going to tell you a story that after we did all the theory, I want to do an experiment. As I'm a theorist, I have no lab, and therefore I go to my colleague and say, "Can you do an experiment for me?" And my colleague will say, "No problem with them." But then, after a few hours, he come back, and because I told him that please make this for me, and a few hours back, he said no problem. About 5 hours later, he said I'm crazy because no one can make those materials. And so in order to demonstrate something, so the next step is that I make something that is simpler. And it turns out that to make something simple is not simple. Okay, so I take a big detour. And so the first thing we do is that we say, we have done, other people have done radial transformation, I have done an angular transformation, let's do some other kind of transformation, let's do a shifting transformation. So I do a mathematical transformation so that all it does is to shift one coordinate by a certain units, say t equal to 2 or 4, okay, so the coordinates become something like this. And then you crunch out all the math, it turns out that you can prove that this is equivalent, this transformation optics, a material transformation that you can have this layered material, that this is exactly equivalent to the voltage transformation. And with the transformation optics methodology, in fact, I will know exactly how to align these layers and what the material of these layers should be. And so you will see later why I'm going to do that. And so with this to say that what does it do for you? So what does it do for you is that, for example, light coming in, and I put the material there, okay, according to this prescription, what it does is that it shifts your wave by a certain method t, and the t can be decided by you. And so this is, we put the simulation of the material in, and here we put in just simply the shifting coordinates so that they are indeed equivalent. And they have to be, because they are designed by coordinate transformation. And of course, you can put a t to be a plus number, minus number, and therefore I can shift it up, you can shift it down, and you can do all kinds of tricks with that. And you can even put the beam and split into two. Okay, you can do all kinds of funny things with that. And in fact, you can even use that to make a what we call one decode. For example, I can put in a material which looks something like this. Shift up, and then the other half phase shift down, so that I have a shift up, shift down, shift up, shift down. And you can see that in that case, then in fact a certain domain is being avoided. And therefore I can hide an object there. I'm not going into detail. It turns out this object is not a perfect clock, but in fact the cross section is equivalent to a line. Okay? And therefore I can just reduce the cross section by using this type of transformation. But the point of doing all this is, in fact, after a lot of mathematics, we found that the rotator that I have, the very complicated parameters, can in fact simply replaced by a spiral shell. Okay? The math is a little bit nasty, so I'm not going to talk about that. But in fact, this will give me the same effect as rotation, because as a rotation can be regarded as a shifting in the angular coordinates. And so this is a numerical simulation that with this I can do the rotation. And of course, in the strict sense, I have to have many layers before I can achieve the effect. If you choose to be more discrete, and then you will lose some of this effect. And so the next thing is that I show this to the experimentalists, and they still think it's too complicated. Okay, and then we do some further reductions, and what happens is that eventually we come up with something like this, which can kind of emulate, not exactly, the effect. And so this would be the true effect, and this is what you get if you have this effect, but you can still see more or less the rotation there. And therefore this sample was really made, and this was measured, and so I'm going to show you the measurement results, and this one. And then so you can see that indeed the fields are being rotated by the device there. And we designed with 30 degrees, and in fact it works very well. And this is another proof that you use a very small dipole, and you can measure the field outside. That you can see that the field is maximum is aligned at 0 degrees, both inside and outside. But inside here, which we purposely designed rotation at 30 degrees, you will see that the field becomes maximum, okay, when the field is 30 degrees. So in fact, this can bring to the rotation. So I just want to show this for two purposes. The first purpose is that a angular rotation, in fact, a transformation optics transformation on the angular coordinates would create an illusion for you, so that you will thought that the world has rotated by a certain angle. And there's no way that the inside and outside observer would know that someone has done the rotation. Okay, you don't see that. Okay, and your eye will see something. I mean, I have such a crook of arm myself. In fact, you would not be able to determine what exactly is my orientation. Okay, so this is something. And just want to show you that in fact it can also be realized experimentally, except that doing experiment is way more difficult than to do the theory. You can do a lot of work. Okay. And in fact, the theory takes about a month. The experiment takes over a year to do. Okay, by design and realization. And in fact, we also have a collaboration with a group in Fudan University who actually, this group is very famous for doing water wave, and therefore they can in fact do a basically a water wave implementation of this, and therefore for shadow water wave. And what they did is that they have this type of thing that is supposed to rotate the water wave, and what they can do is that they can put it in a dish. It's a big dish, okay, and then fill with water or liquid, and then you can project the light, and then you can project to a screen, and then you can really take a picture. And this is the kind of picture that you can see that indeed the rotator can rotate away from you. So if you want to have more information, you can look at that paper. Okay, and so I've talked about what people talk about invisibility, radial transform. I've talked about angular transform, and now I'm going to go into other kinds of illusion that I can create with transformation optics if I use what we call a negative effective index. So, should I take a break or should I continue? Okay, maybe I should take a break and then I continue next time, and would welcome if you have any questions.
Are there questions to our speaker? Yes.
Yeah. Because as you showed that you put a shell in the electric field, the field will be pushed out. So actually there will be no light going into the shell. So this is totally dark inside the shell. What if you put a lamp into the shell?
You are perfectly right. And so the first thing, let me answer the second question first. Put lights inside, the light cannot go out. They will all be confined inside the interior domain. Light can't come in, it can't go up, and therefore all the light will be inside the domain. But your first comment is exactly correct, because if you read internet, a lot of people will say that, oh, sorry, I'm going the wrong direction. This is in fact very nice. You're exactly correct. That in fact light cannot go into the shell, and therefore in the internet you will see a lot of reports that say, this is Harry Potter's invisibility cloak. Strictly speaking, it is not correct, because if you read Harry Potter's book or see the movie, Harry Potter is a cloak in which once you put around himself, you don't see him, but he sees you. But for this particular invisibility cloak design with transcendental media, since no light enters him, you don't see him, and he don't see you. So he'll be an entirely blind Harry Potter. He don't see anything. He just bump his head against anything and kill himself. Okay. And so, in fact, in the next talk, I'm going to see how I can find a way to get around that, so that I can have a device in which you can't see me, but I can see you. But it requires an entirely different way to do the invisibility. But your comment is exactly correct.
Are there more questions? Yes?
What are the experimental limitations on the wavelengths of light use materials?
Oh, I'm going to talk about it next time. It is very, very tough because most of the experiments are done in the microwave. Because first of all, easy to make those very funny structures, and secondly, in microwave, the absorption is very small. Once you go to high and high frequency, the intrinsic absorption is going to be big. Now, if you want to be invisible, the first thing is to not want to absorb. Because once you absorb, I know that you have taken in something from me, right? And how to get around with the absorption is very difficult. But I'm going to tell you near the end of the next talk that there's some really truly ingenious way to do that. There's some experiment from UC Berkeley that can do it with silicon, and silicon is not that absorbing optical frequencies. They can still achieve the invisibility. But I'm going to talk about it next time.
Anyone more question?
Yeah, for the EM wave, you have two freedom. One is K propagation direction, and the other propagation. So, in my opinion, the transformation is control the direction of K. So, you also show you can control the correlation state. How can you do that?
Oh, sure. For the second part of rotation, I'm still rotating the K.
Okay, but how about the correlation is linked with the K?
Well, the answer is yes and no, because if you have the transformation media, because it works not only for geometric optics, it works even exactly in the Maxwell equation. And then what it does for you, for any polarization, if it works, then that polarization, now inside the clock, you don't know because it do all kind of funny things, but outside, the polarization will be preserved. It will be exactly the same as what will come in. Okay? So there's no change. But inside, of course, polarization can change myself. But outside will come back.
Are there more questions? If not, a very naive question. When do you think it will be possible to find one of those box of invisibility, just like we bought a lot of funny shaped hats yesterday at the Great Wall of China?
I really don't know how to answer that question because if you asked me the same question just 1 year ago, I will just tell you honestly that I don't even think that invisibility of this type can be realized at optical frequency. But this year there are already a few experiments that realize that. And so if you ask me today, honest my answer is that I don't think you can buy anything commercial with this in near future. But I could be wrong, but just in the next 12 months I really don't know. But I think, I guess if you want to go to war with this one, it will not be a very good idea, let me put it this way. Because these things are very complex, very delicate. If they want to go to war with it, you want something that you drop it, it will break. And this, you drop it, I'm sure you will break. But for peaceful purposes, something that is commercially viable as a device and so on, I can't do.
More questions? If not, let us thank our speaker again. I want to make a short. One of the options for lunch for students is simply to go to the place where we had the welcome reception. It's very close to this, our conference site. And there are